Okay, so yeah, now let's get the genie out of the bottle. So we want to know how we can make this sampling genie. And the sampling genie, I define it, as I told you, this is the kind of algorithm which is going to take the energy model and it's going to sample from the Boltzmann distribution for us. Now, as I told you initially, one hint, I also put it in the footnote in section 1, that I told you that sampling from a distribution is an exponentially hard problem because we need to consider, exponentially large number of points or computations to do that. But you should keep it in mind that we were talking about direct sampling. And by direct sampling, I simply mean that I get my distribution and I want to just generate one sample in one shot, right? So I'm going to get multinomial like the example we had. And then I sample one uniform distribution, I pass it through the thresholding function, immediately it's going to be multinomial, right? This is direct sampling, just one shot. And if you want to do one shot, it's going to be exponentially hard, right? Now, the point is that I can do nothing about this. This is going to remain exponentially hard. But the point is that I can somehow come up with approximate approaches which approximate sampling from the distribution with lower complexity, usually polynomial complexity. They are not still very charming algorithms, but still they are doing the job. Okay? So the point here is that we can do nothing about direct sampling, so don't think that I'm doing any magic. I know I am capable of lots of magics, but this is not the one which I can do. If I could, I wouldn't have been here, right? So I could solve NP-hard problems. I cannot do that. But we can just come up with some approximate approaches, right? Which can somehow do the sampling approximately or iteratively for us. The most well-known algorithm is the one which are based on this, Markov chain Monte Carlo algorithm. And the idea here is quite simple, okay? So what is the idea here? The idea is that we make a Markov chain, and you do know what is the Markov chain, right? What is a Markov chain? I start with one random variable, right? I'm going to compute the next random variable based on that, right? Maybe I do it deterministically, I pass it through a function. Maybe I do it randomly. Maybe I add one random thing to it, right? Whatever. So I get x0, I do one process, either deterministic or random. On x0, I'm going to get x1, right? Once I got x1, I forget about x0, right? I'm going to do some process on x1, I'm going to get x2, right? And I keep on going, right? So this is what we call it Markov chain. Each time, you only depend on your previous one. It doesn't mean that you don't depend on whatever before, but the previous one is enough for you to go further, right? So if you want to generate x2, you only need to look at x1. Definitely x2 is going to still depend on x0, but you don't need x0 to process, right? You get x1, you process it, you get x2, right? So this is what we call it Markov chain. And the idea in MCMC, Markov chain Monte Carlo algorithm, is that you start with one x0, which is easy to sample, right? Maybe d-dimensional standard Gaussian, right? Everything independent, quite easy to sample, right? You start with a very simple distribution to sample, and you sample it. Then you somehow design one mechanism which is going to progress over time, and gradually it's going to converge to the distribution you want. You get the idea? So this is a kind of iterative, a progressive form of making your sample, right? So I just generate one noise, one Gaussian, and then I'm going to process it, maybe do some operation on it, and I do this operation step by step, right? Till I get to the final point. And then at some point, it's going to converge to the distribution that I want, meaning that that particular sample that I have processed is essentially looking like a sample from the target distribution. Everybody's cool? So this is what we call it Monte Carlo Markov chain. Markov chain, Monte Carlo, MCMC. And one example, which is the famous example we use in diffusion models, we're going to see this once again, is this guy. Yeah? What do? I am generating one x0 here. X0 is generated from any distribution that you want. Yeah? It doesn't matter what the distribution is, right? So you generate that guy, and then that x0, I take it, I might multiply it by square root of 1 minus epsilon, right? So I'm going to give a tiny epsilon power. I'm going to reduce a tiny epsilon power from x0, and then I add this power in the form of a Gaussian noise. Yeah? I'm going to add up the square root of epsilon times a random Gaussian, right? So you see, I get x0, I just do something on it, this is the first term, and then I generate randomly one Gaussian, multiply it by square root of epsilon, and add it to that, right? Now I'm going to get x1, right? Now that I got x1, I'm going to build x2 with the same strategy from x1. So I'm going to get x1. Again, I shrink a bit of power, so I'm going to reduce a tiny bit of epsilon power from it, and then I add it in the form of a Gaussian noise, right? And I keep on doing this. What do you expect to happen if I do it for a long time? I mean, obviously, the power of this xt is not going to change, right? Because each time, I'm going to reduce the power with epsilon, then I add the power as a Gaussian, right? So the power is the same, but the distribution is changing, right? Each time, the power of the original distribution is shrinking, and the power of Gaussian is just increasing, right? And then what's going to happen when I go long in time? Go Gaussian, right? It's going to be completely Gaussian. So if you keep on doing this, when t goes to infinity, when you have done so much of this process, you're going to end up with one sample, which is essentially Gaussian sample, right? Now, you might tell me, okay, Gaussian sampling is not a hard thing. I do agree, but the point here is that I just wanted to show you how MCMC is working, right? So you essentially can make one Markov chain, which is going to push any distribution that you have towards a Gaussian noise, right? We're going to see this guy when we get to diffusion models. Questions? So you got the idea, right? How we do the MCMC. We just start from one point, and then we keep on doing the Markov chain process on that, right? Okay. Now, you can have bunch of sessions on sampling because it's a big thing. I mean, for a long time, people have done it in statistics, but essentially, we don't need all of them. So here, I'm going to just mention two major algorithms which are important for us, namely the Gibbs sampling and Langevin sampling. These two are the main things. We're going to use them later on, especially in the diffusion modeling. So, but in general, there are tons of them out there, right? And then among them, you can roughly somehow classify them into multiple groups. So one group are the zero-order MCMC algorithms. So what are the zero-order algorithms? They essentially just look at the distribution, right? So you would say, I have this target distribution. Maybe I have it completely. Maybe I don't have it. I have some expression of it, right? Sorry, some energy function of it. It doesn't matter. We're going to see one example. So you're going to give whatever information you have about your distribution. It's going to use only that distribution. So you're going to use the density function of the target distribution to generate, right? Nothing else. So this is the kind of simplest algorithm you can think of. And the most famous one is the Gibbs sampling. So Gibbs sampling is a zero-order sampling method. So the good thing about these algorithms is that they only need the distribution from you, right? They don't need extra computation. And they're going to build the Markov chain based on that. But the bad thing about them is that they're going to take quite a long time to converge. Meaning that typically in these algorithms, what you can show is that when you start with one initial point, you're going to asymptotically in time get to the distribution you want. But of course, you cannot wait forever, right? You're going to stop at some point, right? And then the question is how fast it's going to start looking like that distribution, right? Getting close to that distribution. And these algorithms are going to take quite some time to get there, right? So it means that that t in your Markov chain should be quite large. So this is the bad thing. If you want to improve it, you can go for the first order algorithms. And what are the first order algorithms? They not only use the density function, but also, or maybe not only not the density function at all, they are going to use the gradient or derivative of your density function. Yeah? So one order derivative, this is one order of computation, right? Because if you give them the density function, it needs to compute the gradient, right? So one order of computation. More computation you are doing here, but they start to converge faster. Yeah? So a classic terminology here is that they say these guys are going to mix faster than these guys. And by mixing, it simply means that you start from x0. It doesn't look like the sample you want, but it starts to mix with the whole process such that it starts to look like what you want, right? And then this mixing, it simply means how fast it's going to start looking like what you want, right? So these guys are mixing slower, but they take less computation, but this one is taking more computation. Of course, they mix faster, right? So the most famous guy is Langevin here. Langevin is like a very old physical description of the motion of particles, and then it turns out that to be a very good dynamics that we can build something to some Markov chain to sample from a distribution. So we're going to talk about this one as well, this algorithm, because this is very crucial when we get into diffusion models to understand the score matching. And then you can, of course, go higher, right? You can take more derivatives, but you can guess this is like extremely expensive in terms of computation. We don't like them, right? So the things that we use typically are zero order or first order. If you could make it by zero order, it would be great, but typically we cannot. So we typically stick to this first order. Okay, so that's about the algorithms that we could have. And as I told you, you can open many books on statistics, and they have a bunch of chapters on sampling. You can read them through to understand all of not only MCMC approaches, other approaches, but I'm not going to explain those stuff because it's not a statistics here, right? So I'm just going to give you the overall algorithm so that you understand how they do the Markov chain processing. So the first algorithm that we want to talk about is the Gibbs algorithm, which is a zero-order algorithm. So how does it sample from one particular distribution? Well, it's going to start from one initial sample, and this initial sample could be anything, okay? So you're going to take one easy sample. Typically, we take a Gaussian noise, right? And you might have heard it, right? Like people who are talking about generative models, they say, you start from a Gaussian noise and you converge to the image, right? That Gaussian noise is essentially the thing that you start with for sampling, right? So you just start with a simple to sample process. Gaussian noise is the most simple one, right? Or maybe uniform noise, I don't know. Whatever you want, you can start sampling from that. And then you're going to start doing this process. What is the process? You go inside a loop, the time loop, okay? And inside the time loop, you have another loop. That loop is actually over the entries inside your X, okay? So your sample X has D dimension, right? So dimension 1, dimension 2, till dimension D, right? Now, what you're going to do, you're going to loop over them. And you start with the first dimension. I'm going to sample the first one, right? But when I want to sample x1, the first entry from that distribution, that this PW is the target distribution that I have, I'm going to marginalize it, or I'm going to condition it to whatever I'm not sampling. You get my point? So I am doing the sampling for x1. So I should sample the conditional distribution px1 given what? x2, x3 till xd, right? What if I want to sample x2? Then what should I do? P of x2 given x1, x3, x4. You got it, right? So it's going to be xi given anything before I and anything after I, right? Everybody's clear? So you're going to sample anything before I and anything after I, right? So you get your X, you condition it to anything else, and then you sample from it. Once you sample it, you're going to update your sample, that entry, and you go for the next one. You clear, right? Now, one thing that you see here is that for x's which are smaller than I, I'm showing t, but for larger than I, I'm showing t minus 1. Why do I do that? When I am at time t, what is the first guy that I'm going to sample? x1, right? At time t, correct? Then, when I want to sample x2, what should I put as the condition for x1? The most recent sample, right? So x1 already had been sampled in this time, correct? So I'm going to put x1t, but for x3 towards the end, I don't have yet the updated sample, right? So I'm going to take the sample from previous time, correct? So it's going to be x3 of the previous time. Everybody's clear? You get what I'm doing? You don't look like people that are happy? Yes?
Yeah, I guess I'm still wondering about, like, t is like over a time sequence.
Yes.
T is across our, like we have a d-long vector, I guess, right?
Yes.
Why are we doing, like, both of them at once? I guess I still don't get the second loop.
Why we don't do both of them at once?
No, like,
The whole d at once?
no, why is it nested like this?
Because, I mean, every time that I want to sample, generate a sample, I need to go over all of my dimensions. I mean, here, I cannot do this in one shot because in each conditioning, I need the other guys to be in the condition, right? You get my point?
I sort of do, but won't this also be like, I mean, this also seems like a lot of work, even though...
Yes, it is. I'm going to explain it. It is, but it's not exponentially hard. It's polynomial. It's a big drop from exponential to polynomial. But you're right. This is not an easy thing. Still, it's not easy, right?
Okay.
Yeah. It's still a lot of computation, but I mean, it's something feasible, like with very good computation resource. But exponential is infeasible, right? This is the difference. Yeah. Yeah. Yeah.
So if we think about this xi, can I think it as like an image or something?
Xi's are the pixels of the image, right? Oh, this is a good example. I'm going to show you one example for the Boltzmann machine, but Xi's here are the pixels. X itself is the image, right? So you start with the Gaussian noise, and then in the first time, you're going to update your first pixel, right? Then you go for the second pixel, so on till the last pixel, right? So this is one time, right? And now you get this new guy. Again, you go over the pixels, right? So it's exactly like the autoregressive form that you do, right? But in autoregressive, you always condition to the previous times. No, you condition to anything else, right? It's the difference. So in the autoregressive one, you don't have the green term, but now you have it. Yes?
Can we also take xi of the previous time point as our condition?
No, you don't, because you cannot condition yourself, the pixel to itself. Yeah.
Even it is generated?
Yes, even though, yeah. Yes?
So for the green term, why not condition all the xi of the previous?
Sorry?
The green term.
The green term. Why we don't put it t?
Why we don't condition all pixels of the previous time?
No, it's the future time. I mean, what I'm doing, I'm looking at xi, one particular pixel, and I'm conditioning it to anything else. So x is smaller than I is the previous time, not previous time, previous dimensions. X more than I are the next dimensions, right? So it means that I'm looking at this. Okay, maybe, okay. So I'm thinking of this x in this form. So this is your x, right? This is your x, and this is going to be x1, x2, x3, and so on, right? Now, if this guy is xi, if you think of this to be xi, then anything above here is x is smaller than I, and anything below it is x larger than I, right? So what I do at time 1, I start with the first guy, right? I update this, then I go for the next one, and I condition next one to whatever I have, right? But this guy is already updated, right? So when I am at time t, this guy is already at time t. But this one is not yet updated, right? So whatever I have here is from previous time, right? T minus 1. So I'm going to keep here t minus 1, but here I have t, so I can just put t here, right? You get it? Questions? Yes?
I'm sorry, so this whole process is kind of like autoregressive process?
It's not exactly autoregressive because it's not.
Because it needs to generate like each pixel by sequence?
It's sequential, you're right. It's sequential, but it's not autoregressive in the term that you also take the future pixels into account, right?
For the previous time step, it's not.
Yeah, okay, in that sense, yes. In time, when you look at in time, yes, you can somehow say. But the point is that within one image, you are again generating it sequentially, right? You cannot do it in parallel. Yeah. Questions? No question? Okay, so this is, you keep on doing it for multiple times. So you get your first vector. So you started with x0, you just update it once. Then you go for the next time, and so on. And then you keep on doing this till the time has passed what we call it burn-in time. And what do I mean by burn-in time? Burn-in time is essentially the time where the distribution of this xt starts to somehow look like the distribution you want. Well, you might tell me, okay, how can I find that guy? Okay, I cannot say it, right? So it's a kind of intuitive thing. You put some big T to just make sure this is happening. Like 1,000 is one example that you can put. And you can see that this algorithm is not that easy, right? Because even though it's not exponentially hard to do this, but still you need to do lots of samplings, right? Because every single time, every single t, you're going over, you loop over your entries, right? Over your dimensions. So you do these samplings within every single time, right? And then if you fix t, and typically t also, that big T should be something large enough. If you, for example, assume that t should be in the order of dimension itself, then you can guess that the number of computations you are doing is d squared, right? So it's not linear, it's d squared. But the point is that it's not exponential, and it's much better than exponential one, right? You can approximate at least the distribution you want. Questions? No question? So you got the idea. I do not expect you to understand why this is working, because you need to have to study the theory behind it. But take it from my side, it's going to work. If you do this, you're going to have this result. Like under some mild conditions on that distribution P, this process is going to converge you to the distribution you want. And this means that if you start from a Gaussian noise and you do this process on it multiple times, enough number of times, then you end up with a sample that you want. Everybody's cool? So as I told you, this is not something obvious. I do understand. It needs some theory. It needs some analysis. We don't need it. If you're interested, you can take a look at those sampling texts to understand. But we really don't need. We just want to know the algorithm. Okay? Great. So now, one thing that you might tell me is that, okay, you have done a nice job in just writing down one algorithm, which is not exponentially hard to evaluate. But the point here is that you're again using PW, right? When I want to do Gibbs sampling, I'm doing PW, right? PWXI condition to anything else, right? I'm using that one. I'm using the target distribution that I want to sample from. But the point was that in our case, we didn't have access to the target distribution, right? We could not. We need partition function. We don't have the partition function. We don't have the target distribution. The point here is that essentially you are not working with the target distribution itself. You're working with the conditional version of it, which is, first of all, one-dimensional, right? So P of xi given anything is one-dimensional, right? One pixel is being sampled. that is easy, but these samples together is hard, right? This is the first thing. The second thing is that I am doing conditioning, and when I do conditioning, you can see it, that conditioning is the joint distribution divided by the marginal distribution, right? And then the partition is going to cancel out. So I'm going to show it right now for the Boltzmann case. This is going to cancel out. And because of that, you essentially can do this sampling. You can compute those conditional distribution without knowing the partition function. Yes. Okay. So one thing that I would like to mention here is that this Gibbs sampling is quite nice. But again, like the base Boltzmann machine is a quite basic algorithm. So you can do sampling, but this usually needs quite long T, and it's not really possible to modify it that much. Because of that, again, Gibbs sampling remains as a kind of toy sampling, but in some particular examples, you can do it. Okay? So just as a note here. Any question? So you got the idea of Gibbs sampling? Okay, so now that you got this one, let's try it for the Boltzmann machine. So the Boltzmann machine was the machine whose energy function was that quadratic form, right? And what I want to do, I assume that I have trained this model. So I have a particular W fix, right? And what I want to do now, I want to sample from the Boltzmann distribution, which is described with this energy function. Everybody's clear? So the Boltzmann distribution of this energy function, I can write it down. I'm going to show it now. Yeah? And I want to sample from that one. Knowing that X could be a large dimensional, I'm going to use Gibbs sampling. Everybody's cool? Okay. So few things you should remember here. First of all, if I want to write down this guy, I can write it down in this form, right? So this is just expansion. You don't really need to care about it here at this point. The point that you should remember is that, first of all, this W is symmetric. So we talked about it, so I think it was, yeah, here. So we talked about this is symmetric, right? This guy and this guy is the same. This guy is 0, right? Since this guy is 0, I have written here L is not I, right? So you don't have xi times xi. It's not showing up. Because xi times xi should be multiplied with the entry wii, which is diagonal entry is going to be 0, right? So this is the first thing. And the second thing is that my x's are binary, right? My x vector is a long vector, but every single entry inside it is either 0 or 1, right? So if I want to write down the Boltzmann distribution, this is going to be the Boltzmann distribution, right? E to power minus that guy, and that guy only depends on the matrix W, right? Divided by the partition function, right? This is the Boltzmann distribution, and I want to sample from this distribution using Gibbs sampling. So how can I do that? I need to know this guy, right? I need to know the conditional distribution of one particular binary entry inside my vector, given anything else, right? Now, what is the definition of this distribution? P of x given y. How can I write down P of x given y? What is P of x given y? Can you tell me the definition? P of x and y divided by P of y, right? This is the definition of the conditional distribution, right? Correct? Everybody's cool? Right? So I want to do the same thing. So it's going to be P of the blue guy and green guy are the y here. So I'm going to keep that. And the red guy here is the x, right? So I'm going to put it there, right? the joint distribution of all of them, right? Divided by P of only the condition, right? The blue and green. Clear? Now, the denominator, what is it? It's P of x, right? The complete vector, right? Because anything before I itself, anything after I, so it's the P of x, right? P of the original vector. So that one is not a big deal, but the other thing I need to compute, right? P of everything except entry I, right? But how can I compute P of anything except entry I? Now, you tell me here again, what if I want to compute P of y? I want to compute P of y from P of x and y. How can I compute this? What should I do? Marginalization. Sum it up over x. Great. Yeah? So I'm going to do the same thing here, right? I should marginalize. And I should marginalize over what? xi. And how many cases does xi has? 2, yeah? xi is one entry, right? It's binary. It's either 0 or 1, right? So I can use marginalization. I can say this P of x before I and after I is essentially the P of the whole thing marginalized over xi, right? And xi is either 0 or 1, right? So I'm going to put xi once 0, once 1, and then I add them up, right? It's not a hard thing to compute, correct? Everybody agrees? Yeah? So this PW is again the Boltzmann distribution that I have. The only thing that I have done, I have gone on the vector and put the entry I to be 0 once, and then once again I have put the entry to be 1. I added up those probabilities, right? Those evaluations. And now I want to just take this sum and put it in the denominator, right? Correct? So the conditional distribution that I need to compute is going to be the original Boltzmann distribution divided by this marginalization, right? That's going to be it, correct? Now I have Px, and I do know what is the expression for Px based on the Boltzmann equation. I'm going to put it here, right? So I'm going to put it here. Nominator is the expression for Px. Denominator is the expression first for Px when xi is 0. The other one is the expression for Px when xi is 1, right? Do I need to keep the partition function here? No. If I multiply nominator and denominator by the partition function, then partition function is going to disappear, right? I don't need it, right? So I'm going to have this guy. No partition function, correct? So I do not need the partition function to compute this guy. And essentially, this particular guy is a very simple thing. Why? Because take a look at this expression here and say that I want to compute it at xi equal by 0. Okay? So now say I want to compute it at xi equal by 0. What should I do? I need to put here xi to be 0, so it's going to be exactly this term, right? Right? And then I keep the denominator, correct? So I'm going to put it like this, so xi is going to be 0, and denominator like this. Can I simplify this? Look at the denominator, right? If I divide both numerator and denominator with the expression you see in denominator, what's going to happen? Numerator is going to be 1. Denominator is going to be 1 plus something, right? So let me do that. So it's going to be 1, and this is 1 plus something. What is that thing? Yes? Yeah. So when I put it, it's going to be exponential function again, right? Because it's the division of two exponential function. And as your friend said, this is essentially the sigmoid function, right? 1 over 1 plus e to power something, right? Is the sigmoid function. Everybody's clear? So it's quite easy to compute that one now. So this is going to be sigmoid function of this difference. The difference between f at point 0 and f at point 1, right? And this is not a big deal. Yeah? You need to just get your sample your input vector x, once you put xi to be 0, once you put it to be 1, you pass it through the network, you get two values, you subtract them, and this is going to pass through the sigmoid, right? This is going to give you the probability. Everybody's clear? So if I show this by the difference of the energy at the two different values, 1 and 0, then this is going to be the sigmoid function of that difference function. And that difference function is a very easy thing to compute. Questions? No question? So did you get the idea why I can do Gibbs sampling even though I don't have partition function? Because when you do conditioning, that partition function is going to disappear from the denominator and denominator. Everything going to get easy. Okay? And this is, I mean, the price that you pay instead is that you just keep doing it iteratively, right? To just converge. So now, at the end of the day, as I told you, so this conditional distribution is going to be described by a sigmoid. So it's going to be a sigmoid function for xi equal by 0. And of course, for xi equal by 1, it's going to be 1 minus sigmoid function. It's a Bernoulli distribution. You can easily sample from it, right? You can simply put one, uniform, and then you threshold it. This guy you can easily sample, but the original guy you could not sample, right? So this is the whole story here. And for the particular case of the Boltzmann machine, where we consider this Wx times x, essentially this difference function is going to be even simpler. So it's going to simply be one linear transform of whatever you are conditioning. And those weights are resort of a bunch of weights inside your energy model. So I don't want to complicate it here for you. So if you like, you can take your time at home and check it. But essentially what you're going to do, you're going to look at whatever you want to condition. So anything before I and anything after I. And for every single of them, there is a weight inside your matrix. So you're going to multiply them with those weights and sum it up. So it's an inner product only. Okay? So the difference that you need to pass through your sigmoid is again going to be a linear transform based on your weights. And this is again a very cheap computation, right? You can simply do that. So in that case, then the Gibbs sampling algorithm for your Boltzmann machine is going to be quite easy in this case, right? So you're going to start with any sample that you want, maybe a noise, and then you keep on going in time. Every time you get inside the time loop, and then you make a loop over your dimensions, right? Every time you want to do, you need to just sample from the conditional distribution. And we have seen that that conditional distribution is essentially a Bernoulli distribution, right? The parameters of that Bernoulli distribution are specified by your model, right? The weight W and the x's that you had from the previous iteration. So you're going to put that anything before I and anything after I, you're going to put it inside that expression that comes out of that difference. And then you can compute this. This is a linear computation. You do sampling from the Bernoulli distribution. You're going to get an updated sample, right? And you keep on doing it for every single guy inside the vector, right? The first guy conditioned to anything after, right? The second guy conditioned to the first guy and anything after, and so on, right? Once you're over, you have a new updated vector, right? This is one time, and you need to keep it in time, right? You need again do the same thing with this updated vector till it starts to converge, right? And as you said, it's a hard thing to do, right? It's going to take a lot of time, but still, by a fast computer, you can see something, whereas in the original case, you can see nothing, right? That's the difference. Everybody's cool? So you got the idea of Gibbs sampling? Great. So you keep doing it till the burning time is over, and then you're going to have it. Now, since we can do the Gibbs sampling, this is quite easy for us now to train the Boltzmann machine, right? Because if I want to do the training, I just need to replace the sampling genie with the Gibbs sampling, right? So essentially, I start with my data set. I start with some initial weight. When I fix the weight, when the weight is fixed, then the Boltzmann distribution is also fixed, right? Correct? Right. Now I start to do epochs, right? And when I do epochs, in every single epoch, I'm going to go over multiple batches, yeah, right? Or the whole data set. And now, I take samples from the data set. I also take some samples from the model, meaning that I have, I don't know, 1,000 samples. I'm going to generate 1,000 samples from my model, right? And to do this, I'm going to take this W, I give it to my Gibbs sampling. I'm going to say this is the weight that I have for the energy model, right? It's going to generate me a bunch of samples according to that distribution, right? Now I have the samples from the model, and I have the samples from the data distribution, right? Now the rest of things is the same, right? So I'm going to go inside the loop. I just compute the gradient of the energy model at the points of the at the data points and at the model samples. So here I have put this expression here for you because for the particular Boltzmann machine, that gradient is super easy. So you don't really need to do backpropagation. It's a very easy one. But when you have a neural network, it's going to get complicated. You just do it by backpropagation. Okay? But here, I mean, this line 6 is essentially backpropagation over the simple Boltzmann machine. Okay? And now you got your two gradients, one of them at the data sample, the other one at the model sample, and you subtract them. This is going to be the gradient you need to update your model with, right? So you're going to update your W with those gradients, and you're going to get the new updated W, right? What you're going to do? You're going to go for the next batch, right? So you're going to start at the beginning. Again, you're going to give this new updated model to your Gibbs sampling algorithm, right? This is going to generate you a bunch of new samples with this new weight, right? And you use them to do one other iteration, right? So you keep on doing it, and in every batch processing that you do, in every iteration, you need to sample, right? So the Gibbs sampling algorithm, which was not that nice, easy algorithm, is going to just be iterated over and over for training. And you can imagine how time-consuming that's going to be, right? But that's what it is. I mean, we can do nothing about this, right? Everybody's clear? So you got the idea, right? That's great. So now that you have done the training, you're going to, if you do with multiple epochs over your data set, then this weight starts to evolve, and it's going to converge to a point which is a good approximation of your data distribution, assuming that your data distribution is simple enough to be approximated by a Boltzmann machine. Okay? And now once you have this training, then the sampling is quite easy, right? You're going to take the trained model W, you just give it to the Gibbs sampling algorithm. It's going to do the sampling for you. It's going to give you one sample of the model distribution, which is supposedly approximating your data distribution. Everybody's cool?